Welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but want to be its friend.
It's true. I am Corinne Caputo. I'm a writer, a funny person, and a friend to the universe.
Yay! And hello, I am Dr. Moiya McTier, an astrophysicist and a folklorist, and also a friend to the universe and to a Corinne.
Yes, it's true. Moiya is my friend, everyone. and you heard it here first. I'm so excited where we are, Moiya.
I know. Thank you. I'm so glad you suggested this. As my friend, yeah, you should know. This is right up my alley.
It felt very on theme for what we're going to talk about today. We are at the famous medieval times. I don't know what to call it of sorts, but just an incredible, immersive experience where we're going to watch some actors joust. Mm-hmm. And we're going to eat soup out of a bowl, no utensils.
No utensils, and a whole turkey leg.
Yes.
In my hand.
Yes. The last time I came here was with my family, and my mom poured herself a glass of what she thought was water, but it was the soup pitcher, because they serve soup out of pitchers, not out of... I don't know, a soup bowl, you might imagine.
Right.
And the guy was like, he made a face, and he was kind of like, it happens all the time.
Of course it does. No one's expecting a soup pitcher.
It was very funny. But I have to say, in my memory, this place was a lot bigger. But I was in 5th grade, I think, the first time I ever came here. So it felt like a truly massive arena.
It's still pretty big.
It's still fun.
They're riding actual horses down there.
And it's fun now to be old enough to get like one of the fun drinks. Because you couldn't do that when you were in 5th grade.
No, you couldn't. But we'll take advantage of these fun drinks now. Whatever fun means to you. But you said this is fitting for what we're talking about today. Why is that, Corinne?
So to me, it's because this place is for all ages. It's for all ages. You can be young and obsessed with it. You can be old and entertained. You could be right in the middle and your parents are dragging you to some kind of hangout. But I think there's fun to be had for anyone.
I love that. I love that interpretation. I also like it because this is where, like, old meets new, and so it's doubly appropriate for what we're talking about today, which is, how do you tell the age of a star? How do you age a whole ass star?
I think you cut it in half and you count the rings.
Count the rings. Yes. You get yourself a sun sword and you cut it in half.
And you kill it, but you'll know how old it is.
No. Fortunately, there are more humane ways to tell the age of a star. Also less direct, because, spoiler alert, everyone, we cannot go out and physically chop a star in half. That would be really difficult.
But we can try.
And really expensive. We can try. But until that day, we have devised subtler, maybe more indirect methods of aging a star. And I actually love this topic because I took a whole class on it in grad school. I took a whole seminar on stellar aging methods with Dr. Marcel Agueros at Columbia. He's a very smart stellar astrophysicist. And we basically spent an entire semester working our way through a single paper. This is a paper from 2010 by David Soderblom. It is also a paper that I referenced heavily when researching for this episode. And we spent an entire semester going through this paper, talking about all of the different methods, and the paper was written in 2010. I took the class in like 2018 or something, and so we also talked about how the field had advanced in the time since. It was a really fun class.
That's really cool.
It was small, like all of my classes were. There aren't a lot of astrophysics grad students, and we each had to present on a method that we chose. I chose the lithium depletion, which we will hear about closer to the end of the episode, but I did a whole presentation on that to the class. Got an A.
Yes, you did.
No big deal. So I really like this topic. How do you feel up top about discussing the ages of stars?
You know, I haven't thought about it. I feel like I'm going to feel overwhelmed at how old things are.
Oh, okay.
But maybe not. I don't know. I'm excited to learn how old stars are. I've never thought about it. I'm just like, I think things get to a certain age and it's like, that's old. Like, it's just kind of getting lumped into a category. Like when you're a kid and like you're like, this old teacher said whatever, 20 years later, you're like out of college and that teacher's still teaching and you're like, if she was old then, like how old is she now?
20 years later, you realize that teacher was like 27.
Exactly,
you know?
exactly. So I think I've lumped all stars into the same category.
You know what? You're right. You are right. When it comes to lumping, when it comes to like logarithmic categorization of things, you're absolutely right. We can't just lump all of the stars into old. They are all old compared to anything any of us have ever experienced.
Yeah.
Or encountered. Yeah. Do you know how old the sun is?
No, I know it's older than me.
Yes.
I don't know how old the sun is.
Okay, cool. That's a great place to start. Because the sun is actually the only star that we like really know the age of. Everything else is based on models that have been calibrated to our understanding of the sun, or it's based on our best guesses of how things should evolve inside a star. But the sun is the only one we know really well because it's right here in our backyard. We can study it up close. But for a long time, it wasn't obvious how old the sun was, or even how old the Earth was. And I'd say it's only in the last 100 years, less than, that we have started to actually understand how old our solar system is. So it's... A lot of people assumed that the Earth and the sun were the same age, or maybe they would have assumed that the sun came a little bit before if they were influenced by some religious texts that talk about how like the light was created and then the world was created, or maybe vice versa, if like the world was created and then someone said let there be light or something. So but like around the same time, the sun and the Earth and things in the sky would have been created kind of simultaneously. And there are some interesting ways that people tried to estimate the age of the sun, even in like the era of science. So let's go back to Isaac Newton. People think about Isaac Newton as a really smart dude.
Yeah, I was told that.
Yeah, he came up with some cool laws about how gravity worked, about how motion works in general. He also took a stab at estimating the age of the sun and the Earth, and it is
I don't know why I'm going to guess it wasn't right.
It wasn't right. Maybe my little giggle.
That's so funny.
Has something to do with it.
You got to get one wrong. He got all that other stuff right.
Yeah, you can't be good at everything.
It's so
It would
true.
just be unfair. So Newton was estimating the age of the Earth and the sun by trying to figure out how long it would take a molten chunk of solid iron to cool down, because they understood that the Earth was made of a lot of iron. They also probably understood that it was like hot before. I'm not entirely sure how. Like I don't know the timeline of this understanding, but he was trying to compare a molten chunk of iron to the Earth, or at least the early Earth. And so he was using data and measurements that a lot of alchemists used, trying to figure out how quickly iron could cool. And he scaled it up from the size of whatever you can hold in your lab to the size of the Earth. And he was trying to figure out how long it would take a chunk that big to cool down. And that depends on the size of the chunk and the difference in temperature between the chunk itself and its surrounding environment, because that difference is going to determine how fast you draw heat from the object.
Sure, yeah.
And his estimation was that the Earth, and therefore the sun, were about 45,000 years old.
Okay, I know that's not right.
You know that's not right.
I know that's not right.
Is the true answer lower or higher, Corinne?
Much higher.
Much higher. There you go. Okay, so you have an idea.
Whew, I passed.
So that's Newton in like the 1600s is when he was around. And then in the 1800s, we have a German scientist, Hermann von Helmholtz. And he thought that we could measure the sun's age by measuring its energy output, because surely it must be a finite energy source.
Yeah.
It can't go on forever. And so he imagined at first that maybe the sun gets its energy from a chemical reaction like burning coal. We know that it produces heat and light. We also see that burning coal produces heat and light. So maybe the sun is just that, but on a giant scale. And so he calculated how much time it would take to burn through an amount of coal that would be like the same size and mass as the sun, as they had measured it. And it was like 5,000 years, which is clearly not right. Like, even then, they were like, nah, that doesn't make sense. That was less than the estimate for how old the Earth was. And they were like, the sun should not be younger than the Earth. Yeah. They knew enough about space by then to know that. So then he switches his hypothesis. He's like, well, maybe the energy from the sun is actually coming from gravitational collapse. When you have an object that is experiencing some gravitational pull, it has what we call gravitational potential energy. It has like stored energy inside itself just by nature of being within a gravitational field. And if it were to like come closer to the center of that gravitational field, then some of that energy would be transferred into like kinetic energy or to heat or something. So maybe the sun is contracting and all of that shrinking means that the energy is getting converted into heat and light.
Okay, cool.
It's an interesting hypothesis. And they did the math, and they were like, based on the current energy output of the sun and the current size of the sun, we expect that it should be about 20 million years old, which is several orders of magnitude higher than they had before. And so they're getting closer to it, but still no cigar.
Yeah, I think that I'm much more willing to believe that number, but I know I know that it's in the billions. So
yes,
that means that they're really far off still, because as we've talked about before, a billion is not anywhere near a million.
Exactly. A billion is 1,000 millions.
And I don't, you really need to take that in, especially if you're going to live in this capitalist world. You have to understand that a billion is not right.
Yeah, you have to understand that a millionaire, all right, fine, you can make that much money, but a billionaire? No. They are not the same.
I saw, there's a popular old tweet that's like, you just give them an award, say you won capitalism, and take the money.
Yes.
Be like, great, you won.
Here's a little
Congratulations.
trophy. Yeah. Oh, that would be great if that could actually solve all of our problems. Unfortunately not. But congratulations, Corinne, yes. $1 million, it's not enough. Even 20 million, it's not enough. And so they knew that there had to be some other much more efficient fuel source for the sun. And it wasn't until the 1930s that scientists discovered nuclear fusion in the sun and in stars. And so they realized that the sun is much older than we thought it was.
Yeah.
That was more in line with the ages that we were getting for the Earth and other solar system objects. And it was eventually officially confirmed by carbon dating other objects in the solar system. So the oldest objects in the solar system, like asteroids and comets, are good tracers or good proxies for the age of the entire solar system. It's actually, you cannot use that method on Earth rocks. You can't carbon date Earth rocks to try and guess the age of Earth, because rocks on the Earth go through a geological process that kind of remixes everything and takes out that radio carbon dating information.
Oh, cool. I didn't know that.
So we have to study asteroids and comets and meteorites.
That's very cool.
Yeah. So it hasn't even been 100 years since we have known the age of our sun, and now we are trying to figure out how to age other stars, and we're okay at it. I'm going to explain several different methods, all coming from that 2010 paper. And for some of them, we have a pretty good understanding of how big the error bars are on those measurements. And I think you're going to be shocked by some of them. This is not a very precise field of study, but it is improving over time. So coming from David Soderblom's 2010 review on methods to age stars, he splits them up into 3 different types of methods. There are fundamental methods where you are making like a direct observation of something that you know is related to the age, or like really directly related to the age. There's model-dependent methods where you observe some quantities of a star and you plug that into a computer model and it spits out a most likely age for the star. And then there are empirical methods. So we see a direct relationship between the stellar age and something that we can really measure, and it has been calibrated with models. So it's been checked with models. So I have a few different methods for each of those categories, and they're fun. Corinne, if I say the word nucleocosmochronometry to you,
I'm going to think you made that word up.
No, this is not like that game I played with the paper titles. Nucleocosmochronometry. Do you have any idea what that means?
Okay, well, nucleo, I'm thinking nuclear or nucleus. Right. Cosmos. Chronometry, well, chronological, so time. So this is the method of star nucleus aging something, which is just the title of this episode.
Just the title of the
and I'm going to guess that for every method that you mentioned.
That's pretty good. I love when there are unnecessarily long words in science. So nucleosynthesis is the word that we use to talk about when elements were created after the Big Bang. So Big Bang nucleosynthesis tells us that it was mostly just hydrogen and helium, and then a little bit of lithium, and then other elements got produced later. So nucleocosmochronometry is a way of deriving stellar ages by measuring some of those more primordial, nucleocosmo elements. Specifically, isotopes that live for a really long time or take a really long time to decay. So they were looking at the decay of mostly uranium and thorium isotopes. These are tiny little mutations on an atom that over time decay into other mutations of either that same type of atom or a different type of atom. This is why uranium is radioactive, because it is radio decaying into other stuff, and it produces toxic byproducts through that reaction. So these reactions take a really long time to happen, which means we can study how much uranium or thorium isotopes there are in these stars, and that will tell us, how long that object has been around, based on the ratio of normal thorium to decayed thorium. Very similar to how carbon dating works here on Earth.
Sure.
This does come with some assumptions, though. You have to assume how much uranium and thorium were there when the star formed, so the initial conditions. This does work really well for old stars, the stars that formed closer to the beginning of the universe, because they have more uranium, or they have a better idea of the elemental abundances in the early universe than in the later universe.
Okay.
Because earlier in the universe, not as much stuff has happened to deviate reality away from our idealized, simplified models of what happens in the universe.
Okay.
Does that make sense?
I think so, yeah.
Yeah, so we have a model understanding of what should happen.
Right.
Time 0, our model is completely correct. Time 1, our model is fine. Time 2, our model is more complicated, right?
Yeah.
So older stars are closer to time 0. The uncertainties for this method, the nucleocosmochronometry method, so fun to say multiple times. 20% error bars, which means for these old stars that are over 10 billion years old, they're off by 2 to 3 billion years.
That is a lot of time. Wow.
Luckily, we have other methods. We know when we should use nucleocosmochronometry and when we shouldn't. It's really fun to say.
Hey, it's Corinne with a mid-episode break for you. First, a shout out to our patrons. I hope our sun-like stars are super happy wherever they are. Thank you, as always, to Sharon Llewellyn, Finn, and Peyton. And a huge thank you to our latest red dwarf, Torino Flores. Of course, you can support us, hear your name on this pod, and make it to our patron star chart, all by supporting us on Patreon for just about $1 per episode. Find the star chart, Patreon info, and more at our website, palebluepod.com, or by going straight to patreon.com/palebluepod. And if you can't support us financially, that's fine. You are still space. Another great way to support us is to share the show with your friends, and you can leave us a rating and a review right now. And next, I have to ask, are you looking for a fun, no-pressure way to learn math and science? Check out Brilliant.org, the best way to learn about math and science interactively online. Brilliant has thousands of lessons in math, science, and data analysis, and they're adding new ones each month. Enjoy fun storytelling, guided problem solving, and enjoy making lots of mistakes while playing. On Brilliant, your natural curiosity will drive you, not the threat of a test. Brilliant doesn't just teach you facts and formulas, they actually develop your intuition for these subjects through interactive gameplay. Their science courses can help you get a deeper understanding of a lot of the things we talk about on here, like electricity and magnetism and special relativity, or you can branch out to their classes on geometry, foundational logic. Whatever you learn on Brilliant, you'll have a fun time doing it. Go to brilliant.org/palebluepod to get a 30-day free trial, and the first 200 people to sign up will get 20% off their annual subscription. Okay, back to the show.
Another fundamental method, as Soderblom calls it, is the kinematic method of aging stars. This lets us estimate how old a star is based on its motion in the galaxy. So we essentially take the current position and motion of a group of stars, and we backtrack, we trace back their motion to a point in time when all of the stars were closer together, because we assume that they formed together. So when we find the moment in time when they are closest to each other, then that is also their birth time.
Okay.
In general, like the rule of thumb here is that older stars are, and I quote, kinematically hotter than younger stars, meaning the older stars have had more time to spread apart in the galaxy. They're moving faster up and down. They have less predictable circular motion. They are more zippy. That's what I like to call it. So kinematically hotter means they're zipping around more. This only works for groups of stars, because you have to be able to trace back the entire group to their closest point. But it's nice because it doesn't depend on our understanding of stellar physics. Like, we don't have to know what's happening inside the star.
Okay.
We just have to know how stars move around a galaxy, which we know pretty well because it's based on, like, gravity stuff. It gets complicated, so it's not easy, but it is kind of simple in that we have a few equations that we need to use for many stars at a time.
Totally.
I did a lot of stellar dynamics and kinematics in grad school, so I don't know. I'm a fan of this method.
Yeah. I mean, I love the word kinematic. It sounds so fun.
It makes you want to move because it's
really.
it's kinesthetic. Yeah.
Exactly.
Next, we have model-dependent methods. So the first one, actually, all of these methods have a lot of assumptions built in, and they have been calibrated to other methods, or we've checked their accuracy with other methods, so we know how well they're doing. The first model method is called isochrones fitting. Isochrone comes from the Latin or Greek for same time, and so stellar astronomers who also do computer modeling, they have spent a lot of time and effort coming up with models for different types of stars at different snapshots in time and what those stars should look like. So, thousands of models. We've talked about the different stellar types before. There are 7 different stellar types on the main sequence of stars. There are also pre-main sequence stars. There are post-main sequence stars, right? For all of these types, at different snapshots in time, from 0 years to 100 billion years or something, depending on how long the star lives, they have essentially taken a model picture of that star, so that when we observe a star out in space, we can measure its temperature and its luminosity and what the different element abundances in its atmosphere are, and we can plug those into an isochrone model, and it will spit out the most likely type of star and the most likely point on its lifespan. It's amazing.
That's very impressive.
It's very impressive, and it's computationally intensive. Although they do have some relatively easy to use computer programs in grad school. Not in my stellar ages class, actually, but in my stellar processes class, where we had to learn about stellar evolution and how they change over time. We had to use isochrone models to fit an age to some like hypothetical star we were observing. And the one I used was called MESA, like MESA. It's an acronym, of course, but you just put in your parameters, your like description of the star, and it plots out this really nice line, this isochrone, and tells you which one is the most likely. It's cool. It's
that
fun
is
to use.
cool.
The next one is astroseismology.
Okay.
All
Another
of these
crazy
have
word.
fun names. Astroseismology is like seismic activity, the stuff that causes earthquakes here on Earth, but in stars. So we, when the stars have seismic activity, they seem to pulse. They get bigger and smaller and bigger and smaller. Also, like brighter and dimmer over time. And so we can study those pulsations or that seismic activity to figure out like where in its life cycle the star is. And this is based heavily on our studies of our sun, because we actually do have telescopes that measure seismic activity in our sun, and they let us see kind of into the inside of our sun. Kind of like how Toph on Avatar: The Last Airbender, she uses the vibrations to see, because she's blind with her eyes. Scientists have done something very similar with the sun. And then use those measurements to calibrate our observations of other stars. So they're very useful for older and more massive stars, because those tend to be denser, and that means the pressure waves or the sound can travel more efficiently through the star, so we get better measurements. And this method actually has some of the best accuracy for any method we're going to talk about today. Their error bars are usually around 10%.
That's better.
That's better. I didn't say this, but for isochrones, the uncertainties can get up to 50%. You can be like
very high,
half off of the actual answer.
That's very high.
So 10% seems really good after that.
Yeah.
And then we come to the empirical methods. These are where we see a direct relationship between stellar age and something else we can measure. These all work better for low-mass stars because they depend on physical events that happen in a particular zone of the star called the convective zone. And I think we talked about in our stellar types episode that only the low-mass stars have really big convective zones, and when you get to higher masses, then they start to transfer heat through radiation instead of convection. So we're interested in the low mass convecting stars. One of these methods is called gyrochronology, and it's kind of like we're just watching these stars dance. We're watching them dance and spin, and depending on how fast they're spinning or dancing, that tells us their age. The young stars spin or rotate more quickly than old stars. So
that feels on par with humans.
Exactly. I like this because it's intuitive.
Yeah.
The young ones are faster. And so we talk about spin down rates for stars. This is difficult sometimes because it can be hard to measure how fast a star is rotating. You have to look for star spots or other features that actually let you see the motion of the
you
star.
Can track when it's out of sight or
exactly. And it's not like a trivial thing to try to do to measure the rotation of a very distant star. So it can be hard to measure the rotation, but it's also kind of a tricky relationship because we have seen a large scatter or a large variance in the rotation speeds of entire clusters of stars that we expect to have formed at the same time. So there's some doubt for this method. And it also biases towards younger age estimates because we say that young stars spin quickly, so we might just see a fast spinning star and say that it's younger than it actually is. But it is really good for low mass stars up to stars the mass of the sun.
Cool.
And then we can, kind of similar, we can measure its magnetic activity. Younger stars are more magnetically active than older stars, but this is actually really nice because there are a lot of ways to measure the magnetic activity of a star. You can look at coronal emissions or like flares coming off of the star. You can look at the way that different elements are behaving in the spectrum. Like there's just a lot of ways to look at magnetic activity. And then finally, we come to lithium abundance, which is the one I presented on. The infamous lithium abundance. And this is actually interesting because we're not totally sure why this works. But for some reason, clusters of stars seem to form with very similar levels of lithium in their on their surfaces, and they deplete that surface lithium over time. And we're not sure why it works. But it does, and this relationship is especially strong for pre-main sequence stars. So that's a nice way to get ages of stars before they come onto the main sequence.
Cool.
Yeah. And the best way to calibrate all of these different methods, because they need to be checked. So like the way you calibrate a method is, say you have this new lithium abundance method. You have a group of stars that you've already aged with like astroseismology, for example. And now you're going to calibrate it with some other method that is more reliable. And so the reliable methods are statistical, where we take a whole group of stars and we try to measure their ages as a whole population. There's some statistics magic here where the more attempts you have to count something, the lower your error bars are going to be. And so they do this by looking at clusters of stars. And there are two types of clusters of stars. There are globular clusters, which are usually the remnants of old galaxies that have merged into the Milky Way. They're typically found in the halo, and they're typically much older than the other type of cluster. The other type of cluster is called an open cluster, and that's because they break open over time. These are batches of new stars that form together, and through dynamical or gravitational interactions, as that clump of stars moves its way around the galaxy, it breaks apart. Like they spread apart. And so these open clusters are very young. They're usually closer to us, and so it's easier to study them. And so we will calibrate our other methods by comparing it to those cluster ages.
Cool.
And that's a lot of different ways.
Yeah, there's a lot of ways to do it.
Ages of stars, and they all come with their own uncertainty, and it's still like a growing area of research. There were a couple of times when this came back to bite us. Like astronomers were kind of publicly embarrassed about how much we didn't know about stellar ages recently in the news. So one of them is about the star Betelgeuse in Orion. Have you heard of
I have
Betelgeuse?
heard of Betelgeuse from you, but I don't know much about it, and I think it's so funny that it is not spelled the way that you spelled Beetlejuice.
Yes. Oh my God. I recently went to see Beetlejuice the play. Recently, it closed in January, but I went to see it, and they have this big sign on the set that says Beetlejuice, but it's spelled like the star.
Whoa! Why?
I don't know. I was like kind of seeing someone who worked in the props department, and I was like, "Why did you spell it wrong?" And she was like, "What do you mean?"
That's so funny.
So I still don't know why, but it bothers me to no end.
We're gonna get to the bottom of this.
Thank you. Yeah, so it's not spelled the same way as the character from the Tim Burton movie.
Yeah, it feels like a Tim Burton movie, even if it isn't.
Right, at least in spirit. Exactly. But Betelgeuse is in the constellation Orion. It is one of the shoulders of Orion. And back in 2019, it caused this uproar among astronomers because it appeared to be dimming. It was less bright than it had been, according to all of our records. And so people thought maybe it was ready to go supernova, because one idea is that before a star goes supernova, it kind of contracts on itself so it gets more opaque and therefore dimmer before it explodes as a supernova. But we aren't sure how old Betelgeuse
Okay.
is. I saw age estimates that ranged anywhere from 8 to 15 million
Okay.
years. That's a really
Yeah.
big range. And so it's in this funny, fuzzy range of maybe going supernova soon, but we don't know when because we don't know how
Okay.
old it is. Had we observed Betelgeuse being born, one would know how old it is because we would have known
Yeah.
when that happened. But also, when a new star forms, depending on its mass, like its mass determines how long it's going to live. So had we known its mass early on, we would be able to tell when it will go supernova. But we don't know enough information yet. Another time we were embarrassed happened in 2020 when we learned that the sun isn't as magnetically active as we expect stars of this type and age to be. And so clearly we still have a lot to learn about middle-aged stars. And maybe some of these methods, like the magnetic activity method, maybe they're not so reliable anymore.
Twist.
Twist. I think we did all of that, and I didn't even bother to say like why we care how old stars are.
Tell me, why?
Well, first and foremost, it's because they act as timestamps for different events in the universe's history.
Oh, yeah, sure.
So, like, we can't say how old a galaxy is definitively, but we can try and find a galaxy's oldest star and say that that is how old the galaxy is. So it helps us come up with like numbers and ages to talk about galaxies, but it also will tell us when different galaxies collided. During galaxy collisions or galaxy mergers, there's a burst of new star formation because the galaxies are crushing their gas together. So if we could age those stars, then we can learn when that collision happened. There's actually a really cool subfield of astronomy that tries to figure out when mergers happened in the Milky Way's history based on studying these streams of stars that get left over after the merger or collision. So there's this one kind of big merger that we only learned about in the last decade or so. It was a merger with a little dwarf galaxy called Gaia Enceladus, and we have studied the stars that we think are left over from that merger to determine when it happened, and we found out that it was actually a much bigger merger than we previously thought. We realized that the other galaxy was bigger than we thought it was, more massive.
Sure. Wow.
It also helps us understand the evolution of stellar systems, so it tells us what to look forward to with our own sun. It gives us a hint at habitability on other worlds, so like the SETI, the Search for Extraterrestrial Intelligence people, they're interested in this, because if we find a planet that is in the habitable zone of its star, so it's like the right temperature to have liquid water, and it seems like it has an atmosphere, and there's water in it, and blah, blah, blah. If all of those conditions are right, the next question we're going to want to ask is, how old is the star? Because that's going to tell us how old the system is, and whether or not it's had enough time for life to actually happen on that world. So there are a lot of reasons that many different types of astronomers would be interested in the ages of stars.
Oh, that's so fun. Yeah. Everything's so old.
Everything is so old. Maybe that'll help. I don't know. When I turned 25, my 23-year-old friend was like, "Oh my God, you're so old."
Oh,
and
that is the worst.
That's the worst. It's just like objectively not true. But now I'm 28. I'm not old. I still feel like a baby adult. But I know that I have some friends who are like turning 30 or who are in their 30s, and they seem to be very stressed about their age. So maybe this will help. Like, you're very young.
I'm 31, and I felt so much relief turning 30.
Good.
Like, I was more stressed when I was 28, 29 than I was when I was 30, because it was like this impending doom towards age. And then it was just like pure freedom once I'm in my 30s. It's like, well, it's here, and there's nothing I can do about it.
Can't take it back.
Nope.
Yeah, so you're not old. Stars can be a trillion years old. You're not that.
And I hope I never am. If I learned anything from Tuck Everlasting or Twilight or any movie where they live forever, it's not for me.
I would do it.
You would?
I would totally do it.
That's so funny.
Yeah.
I would do it if I could pick who also gets to age with me.
Oh, no, I don't care. I don't care. I don't care. I'll charm new people every 30 years. I don't care.
I think you definitely could, Moiya. And I hope you do. I was going to say, I hope I live to see it. And you know what? I won't.
No. And you don't want to, so it's fine.
No.
If we have the time, I think we do. If we have the time, I thought it might be fun to try and think of these stellar aging methods as like ways to guess a celebrity's age and like which of them would be most effective. Like I think something like gyrochronology, like seeing how fast they dance. Like,
I think you're totally right. And also magnetic activity, like how charming were they?
Ooh.
I feel like they get less charming perhaps
you think
as they get older.
Oh, I would expect that many of them get more charming.
I think it depends on who. I think some people get like curmudgeonly, which totally should.
Mm-hmm.
And some people are more open to meeting new people. But that's okay because not all of these methods are going to have the success rate every time.
Exactly, right? Like some methods are better for low mass versus high mass stars, and some of these methods will be better for charming versus not charming celebrities.
I feel like there's an isochrone model where you like type in like what cultural touchstones this person has.
Ooh.
And then it'll tell you like, okay, they're either like 55 or 42 or like
yes, it's I guess the analogy there is like you say what cultural touchstones this celebrity has, and the isochrone model spits out they're probably the same age as these actors from these movies. So like
exactly, yeah. And the probability of each.
Yes.
Exactly.
One of my favorite ones, the kinematic ages. I feel like that would have something to do with how many movies are they doing at once.
I was just gonna say it's like how many jobs they're booking in a year.
Yeah, and I feel like that actually it increases and then it decreases.
Yeah,
you know.
Mm-hmm.
I feel like I don't know which stellar aging model this is, but like there must be something about like how many drugs does the celebrity use? And can you use that as a proxy for age?
That's so funny. I feel like that one might have a high uncertainty because I feel like when you're younger, your body might tolerate more drugs, but also when you're older, you might do more just because you're addicted.
Yeah, you're addicted. You like have the resources, and you're
exactly
you like know how to handle it. Maybe I don't know.
Maybe I'm not fluent in drug use.
Me neither. So yeah. I mean, I think that there are lots of ways you can tell a celebrity's age, and at least the range of possibilities is much narrower with a human celebrity age.
There's also the famousbirthdays.com as the #1 resource. Let's not forget.
What's your favorite method?
Famousbirthdays.com is so fun because it includes actual celebrities and then like people I've never heard of who are like TikTok stars, I assume. And I'll never be on the side of TikTok where this person exists. They're telling me this is the most famous today. The most famous person's birthday is a TikTok star.
I can't wrap my head around that. There are more famous people these days than I will ever be able to know about.
Yeah, I can't fit them all in my head. And I used to, and I still do. I just love stupid celebrity news, but there's just too much now.
There's a lot.
I can't be invested in everyone's story.
It's too much to be on all the time, and we have to protect our own peace.
Exactly. I can pay attention to the Vanderpump Rules scandal, and that's it.
Okay, yeah, well, I am all for you limiting the celebrity gossip that you take in to protect your peace. But I think that it is almost time for like the big jousting tournament. So maybe we should.
It is, and they're gonna crown a princess.
Ooh, okay, we definitely want to be paying attention for that.
We can't miss it.
So listeners, no matter how old you are, and no matter how old your favorite celebrity is, remember, you are space.
You are space. Bye.
Pale Blue Pod was created by Moiya McTier and Corinne Caputo with help from the Multitude Productions team. Our theme music is by Evan Johnston, and our cover art is by Shay McMullen. Our audio editing is handled by the incomparable Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Twitter and Instagram, or check out our website, palebluepod.com. We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
If you want to support Pale Blue Pod financially, join our community over at patreon.com/palebluepod. For just about $1 per episode, you get a shout out on one of our shows and access to director's commentary for each episode. The very best way, though, to help Pale Blue Pod grow is to share it with your friends. So send this episode, this link, to one person who you think will like it, and we will appreciate you for forever.
Thanks for listening to Pale Blue Pod. You'll hear us again next week.
Bye.